Dear friends, welcome to this new video, almost technical for people interested in some aviation insight. Many people wonder when and how the engines are maintained, but to do that I'll have to go through some parallel information as they become relevant in particular moments. So let's go to it. There are two basic types of aircraft: the airplanes, called fixed wings, and the helicopters, rotary wings. Tilt rotors and vertical takeoff jets are called power lift. The difference is that power lift get the aircraft get to the air by the pure power of the engine and not the airflow flowing through the wings to get lift. Aircraft and helicopters gain lift by laminar flow of air over the wing. Too slow, no lift, slow speed stall. Too fast, high speed stall, no lift. So the propeller of an aircraft is a small wing rotating at a speed to produce lift in front of the aircraft, literally pulling the aircraft forward. The speed and the shape of the propeller have to take into account this concept. The angular speed is equal at any given point of the propeller, as it rotates so much degrees of angle at a given time. But the root and the tip have different speed in distance traveled. Furthermore, anytime the aircraft is in motion, and the propeller is turning, of course, the path of the tip of a propeller blade through the air is a helix, and therefore its velocity, the tip speed, is a vector sum of the rotational velocity plus the translational velocity, or the helical tip velocity. So easily the tip can go supersonic and therefore stalling at high speed and not producing the lift actually called thrust to propel the aircraft forward or give lift and movement to the helicopter. The higher the number of blades, the shorter can be the propeller, avoiding the supersonic onset at the tip. Modern turbofan jets are nothing more than a jet engine with a glorified propeller in front, rotating at a very high speed. Let's talk about the aircraft that fly at subsonic speeds. Commercially, the supersonic is not economical or environmentally friendly yet, as the fuel consumption grows exponentially as we approach the speed of sound, and that's the reason why we are stuck with 80 to 90% of sound speed for commercial aviation since the early 50s. The unducted fan shown here is the development of use of blades to increase efficiency and economy for the commercial aviation. Any modern aircraft uses the turbofan with the engine and all its components encased in a nacelle. Basically, the jet engine uses the same principle of any engine: take air, compress, add fuel, burn the fuel, expanding the air and expelling it. The reciprocating engine of our cars and the piston engines of aircraft have this in 4 strokes at each cylinder. The jet does it in a continuous form. Everything is happening at the same time. The difference is that the propeller pulls the aircraft forward. The compression and subsequent quick expansion produce power that is transmitted to the wheel in a car, and the forward movement in the airplane by thrust or movement of the rotor blades on the helicopter. The jet engine uses the differential pressure to push the airplane forward. Now, why the previous explanation was important? The fan of the jet engines rotates at a very high speed without the tips being supersonic. Once that was achieved, the development was great in efficiency of engines. Jet engines at full power have a very high pressure ratio, some over 40 per 1. Typical diesel 18 per 1, gasoline 10 per 1. Thermal efficiency of the best gasoline engines are now around 38%, while a turbine engine can achieve 65%. Also, the efficiency is due to the number of moving parts. Higher number of moving parts, loss of efficiency, and higher risk of breakdown. To achieve this compression, the air was thrown into a centrifugal and from there moved to the combustion chamber, like the turbos on the diesel engine, like the Goblin engine shown here. The fan engines and the turbofan engines use an axial flow to compress the air with greater efficiency. The air is ducted through the nacelle and compressed at various stages. The fan is moved by the turbines and acts like a ducted propeller, with the air moving around the engine, increasing thrust and diminishing the noise impact of the jet. Then the air is further compressed in a series of smaller plates and forced into the combustion chamber, where it's mixed with the fuel and ignited. Then the expanding air with great pressure makes a differential pressure propelling the aircraft forward. The combustor. Here lives the main cause of life and death of jet engine. This is the hot section of the engine and the one that is consumed quicker than the others, being the turbine blades next. Every engine is born with a life expectancy that can vary according with the usage habits of the operator. This determines when the engine will go out of the wing for revision. This life expectancy is the EGT margin. If you notice the 741 degrees centigrades and the red band, that's the limit. End of the engine life is when the temperature reaches the red band. Piston engines normally are overhauled with an average of 1,500 hours, but serviced at every 50 hours. The jet engine is serviced with oil and small services according with the schedule service furnished by the manufacturer, and overhauled when the EGT margin reaches zero. To achieve that, if you've seen my previous almost technical video, you'll remember that I mentioned the max power flight. The engine should be operated with caution, using less power possible. The performance for takeoff is very important in this lifespan of the engines. Every runway to be operated should be long enough for the airplane to accelerate, arrive at a predetermined speed, where a decision has to be made to continue or stop. In the case of malfunction, and stop on the same runway, or continue and clear the runway threshold by 35 feet. That's called the balanced runway. Of course, the real certification to operate had other safety parameters added on top, and even more in case of weather and or contamination. Everything is based on the International Standard Atmosphere, ISA. Let's assume my aircraft weighs at takeoff 50 tons and the runway is 2,000 meters long, and I need the whole runway for takeoff to achieve the threshold at 35 feet in case of malfunction and continue takeoff, and the meteorological conditions are ISA. So on a balanced runway, I'll accelerate, have an engine failure, and take off, passing the threshold at 35 feet as shown here. Imagine a different situation. The air is cooler or you don't weigh 50 tons, and because you have runway to spare, you can do two things, or a combination. One is a reduced takeoff thrust, the other is a derate the engine. The combination is derate and then assume another temperature. Operation at reduced takeoff thrust is based on assumed temperature higher than the actual ambient temperature. It's permissible if the airplane meets the applicable performance requirements at the planned takeoff weight and reduced thrust settings. The thrust reductions is referred to the takeoff thrust, which in turn can be either a full rated takeoff thrust or derated takeoff thrust. There are rules that apply when and how much you can reduce the takeoff thrust. Basically, you're lying to the engine via the computer that your engine is less power or the temperature outside is way hotter than it actually is. With that, the power applied is less than maximum and the hot section of the engine is preserved. Many operators, as they operate with reduced power most of the time, they have to perform a full thrust once a month to verify the EGT margin. The parameters are permanently recorded, either direct online via satellite or in an airborne storage called QAR, seen here. Quick access recording, where not only engine data is stored and all the parameters of the flight, the same that are stored in the so-called black boxes. These are constantly checked for safety reasons to keep the standards high. Another factor affecting the life of the engine is the balancing. How annoying is to have your car wheels unbalanced? Imagine the rotor unbalanced. The balancing is of the utmost importance for the different parts of the compressor and the turbine, as the blades turn at an incredible speed a mere millimeters of the ring that protects the shroud of the engine. So unbalanced and scraping the walls reduce significantly the lifespan of the engine, being the cause of unexpected failures. Another factor is bird strike, but that's independent of the will of the company and the technical verifications. There are ongoing researches of the parts and components of the engines to mitigate the risk that this hazard poses, not to mention other environmental hazards like volcanic ash or heavy rain and sand. Obviously enough, all this reduces the EGT margin, thus reducing the lifespan of the engine. As a rule, the companies are obliged to follow the rules set by the authorities. The basic rules are issued by ICAO, and the various national authorities decide how to follow in simple manner or in a more stringent form. For the maintenance part, there are two different bodies. The maintenance with the field engineers that verify and physically work on the airplanes, and the compliance department that has the obligation to monitor the engine, airframe, electronics, etc., and guarantee that they are operating within the rules in a safe manner and as recommended by the manufacturer and or the authority. In the European Aviation Authority environment, this is called CAMO, Continuous Airworthiness Maintenance Organization. Thus, the quality department or compliance monitoring verifies through various methods, mainly via repetitive internal audits, via the data produced by the several components, that there are no issues and the various departments are working as they should. The role of the authorities is to guarantee that the various organizations comply with the rules by verifying the documentation produced by the quality assurance/compliance monitoring departments. It's not self-regulated, but self-monitoring by the organization. Obviously, the existence of so many layers in the compliance, monitoring, and the operations have a cost, and the optimization of the costs go exactly via this compliance. Accidents, mishaps, and early maintenance are no good for anybody, and that's the base of flight safety, the compliance. Imagine what is the cost of an accident. Besides of the obvious cost of lives that cannot be measured in money, the financial cost can put a small to medium airline out of business, regardless of the insurance. Aircraft engines and airframes are acquired separately. When an airline acquires an aircraft or an engine, it can be buying or renting, and that is the lease, finance, or lease operational. The compliance to extend the lifespan of an engine is not only a case of costs, money, it is also environmental. Researches in how to reduce the impact of what we humans do onto our planet is an ongoing. So next time you fly, admire the people and the organization you're trusting yourself in. The redundancy, the technical progress, and the preparation, the knowledge, the culture, the training, and security are fundamental bases of the safety in flight. So, fly safe, stay safe, and thank you very much. Do not forget to like my videos and to subscribe to this channel so we can grow and bring more interesting issues with improved quality. The links to my playlists are below in the descriptions. Bye bye.